Welcome everyone to today's chaos. We are very happy to have Sam Hughes, who will tell us about complements of surfaces in simply connected four manifolds. Floor is yours.
Thank you for the invitation. Yeah, so this is kind of a different area of maths for me than maybe normal. When I started this project, okay, good, that's worked. Yeah, so all of this is joint work with Daniel Ruberman, who's at Brandeis. And basically I was, my partner lives in Brandeis, or lives in Boston. So they got wind, the group theorists at Brandeis got wind that I was in town and invited me to come speak. And Danny came on to my talk and was kind of, doing four manifold stuff in the background, and something I said reminded him of some old problem that he'd been thinking about probably 15, 20 years ago. So he said, "Oh, do you want to come and chat about it?" And I said, "Sure." I mean, I'm not sure I'll be able to say anything helpful, but you never know. So we kind of sat down and thought about it for a bit, and we ended up solving this quite old problem from the Kirby list. So that was cool. And it all secretly becomes group cohomology, which is probably why Danny wanted to speak to me in the first place. Yeah, so I'll give you a little bit of background as I understand the problem, and maybe some of your perspectives that perhaps kind of you would have more to say than I can maybe give you, but I can at least tell you what I know about this problem and maybe how we came to it. Yeah, so I'll kind of just recap a few things about four manifolds for culture and then state the problem and solve it, and that would be the talk. So interrupt me with any questions at any point, and let's crack on. So for simply connected four manifolds, I guess the first important result is due to Whitehead in 1949. And this is a very cool result. So you have X and Y are simply connected four manifolds. So simply connected for me will just be SC the rest of the talk. And they're closed, and they're four manifolds. Then they're homotopy equivalent. So X is homotopy equivalent to Y, if and only if some quadratic forms based on their cohomology are equivalent. And we can say what the form is. Well, it's exactly the cut product. So Q of M is just the map from H2 of M with integral coefficients to H4 of M with integral coefficients, and just you send X to its square. Okay, so we have some classification that's really cool. And then the smooth classification turns out to be a lot harder. So the versions of the Poincare conjecture are still open, as you probably all well know. But a result I quite like is that if you look at Friedman's work in 1982, he showed that if you have a simply connected four manifold with this form being equal to the E8 lattice, then actually this thing isn't smoothable. Which is really strange. Yeah, so that's cool. And I guess this kind of became the entry of kind of gauge theory into four manifold topology was sort of around this era, if I understand things correctly, which is kind of what Danny does, I guess. It's less of what maybe I'm familiar with, but I'll say a few words when the time comes. So given something that's quite remarkable, I guess, about dimension 4 is that if you have some X to the 4 is smooth and simply connected, and you have some second homology class, sorry. So this guy, then there exists a surface, a sigma, which is smoothly embedded. such that it represents this class. So the fundamental class of sigma, when you push it forward, is exactly the homology class you first thought of. And there's kind of two things to note. The first is that it's smoothly embedded, so it's not just immersed. So even though this cohomology class might be like a multiple of a primitive, you can actually take a smoothly embedded surface. So it doesn't have to self-intersect, which is always really strange. Like this fact kind of haunts me when I found out about it. It's really odd. So what it says is like you can change the representative in the homology class to find a smoothly embedded one. So you can sort of get rid of the self-intersection points, which is just, it's kind of weird. I don't know. I thought this was cool. But sigma may not be S2. So this is kind of the other thing is like you might have to take some surface with lots of genus. Okay, so I think what motivated a lot of work of Peter Kronheimer and Rauke and many other people is that if you're given some second homology class in your simply connected manifold, what is the minimal genus? What is the minimal genus of some sigma represented in that class? So such that the fundamental class of sigma equals the sigma here. Okay, so I think this is a reasonably well posed problem given the above. And a huge amount of work kind of went into this. So one of the big results is due to Kronheimer and Rauke, where they kind of use gauge theory to do this, or they come up with a gauge theory to do this. And I didn't know what gauge theory was because I come from like geometric group theory, which is very much not kind of PDEs and things like this. So I went and asked someone down the corridor what I should say in a talk to kind of give people something to take away from it. And he said that like the idea with gauge theory basically is you have something that you can understand like topologically, like a connection on like a vector bundle, a connection on a bundle, something like this. And you maybe put some PDEs on it. And the PDEs, hopefully, first, they don't depend on the smooth metric. And secondly, or at least the solutions that depend on the smooth metric. And secondly, the number of solutions counts something. So you count the number of solutions, and this should quantify something about your manifold. So this is kind of the idea. And I said, thanks, that's actually extremely helpful because I've been sliding down a rabbit hole of PDEs and not really knowing what's going on. And actually, this is very concrete. So that's kind of the idea. So the kind of the big thing that they proved, Kronheimer and Rauke in 1993, which predates me by several years. So if you have X4 simply connected and closed, you have I'll write down a few conditions and then I will explain what they mean once I'm done. So you have this B plus of X is going to be at least 3 and odd. The SU2 polynomial invariance. So this is kind of the precursor to Seiberg-Witten theory, I believe. So the SU2 polynomial invariance, non-trivial. And then if sigma G is should be not equal to S2 is a smoothly embedded surface, then 2G minus 2, so the Euler characteristic is exactly it's bigger than the intersection number. So that's really cool. So somehow you go via all of this non-trivial like analysis and PD theory, and you relate the genus of the surface to the intersection number. So that's a really nice consequence. Maybe I'll just say a couple of words about the things in the statement. So here, sigma dot sigma is the intersection form. So you can think of this as sigma cup sigma hat product with X. So this is the intersection form. And B plus is the dimension, it's the dimension of the maximal positive subspace. Of this one. Okay, so that's pretty cool. And one of the other kind of things that they could deduce, and I was speaking to Danny about this, and he kind of said like, this is a pretty easy consequence of what they were doing. And I'm not convinced that it was pretty easy, but maybe it is if you do gauge theory. But I got through the proof anyway, so that was reassuring. So what they prove, and they say if you have x to the 4 simply connected closed, and some embedded surface whose self-intersection number, oops, sorry, my tablet always does this, is square free. So by this I mean like you don't have a square of a prime dividing n, so like 4 doesn't divide n and 9 doesn't divide n and so on. Then pi1 of the complement, so if I just cut out this surface, has no non-trivial SU2 representations. And then they remark that they don't know a single example where the fundamental group of the complement is non-trivial. So I guess there's a few kind of reasons where you might want the complement to be non-trivial. So like the kind of the reason I guess I thought of was in like 3-manifold topology, if you have a knot, say like a knotted S1, and you embed it in the 3 sphere and you take its complement, that complement actually tells you a ton of stuff about the knot, and it gives you this hyperbolic 3-manifold in a lot of cases that's like kind of very interesting to study. So like if you increase both dimensions by 1, you might expect lots of interesting things to happen, and it just, I guess no one had examples where it did. So then a couple of years later in the 1997 Kirby problem list, so Kronheimer in 1997 Kirby list. Asks, so you have x's above, so x4 simply connected and closed, sigma smoothly embedded, and then if the self-intersection number of sigma is square free, is pi1 of the complement ever trivial, or is it always trivial? So this was the question, and I'm quite happy to report that the answer is no, it's often non-trivial. So this is this year. So the answer is no, it can often be non-trivial. So I guess I'll just prove it, because the proof is quite hands-on and there's not too much to it. There's like this standard trick in 4-manifold topology. There's a couple of tricks from group theory that are pretty straightforward. Maybe the worst thing that happens is Bordism, so it's not too terrible. So let's just prove it. So proof, or construction, I guess. So to start with, I'm just going to kind of establish a bit of notation. So we're going to let sigma be a surface. genus G. I guess we want G at least one. N is the disk bundle. How do I spell? What's the US spelling? Disk bundle, it's better. Disk bundle of Euler class N. So, we have some D2, we've got N, and then we have our surface. And then we're going to let Y be the boundary of N. And if you think about what this is a circle bundle over a surface. So this is a Seifert fibered space. And it's one where you have like no singular points because we started with just an honest surface and we've just taken the Euler number to be N. So it's the Seifert fibered space determined by the genus and the Euler number. So that's cool. And just a remark, I guess. We have this notation. If sigma prime is in some four manifold, then x minus sigma with deformation retract onto x minus the interior of N. So here I'm thinking of N as like the tubular neighborhood of my surface. That's so these kind of like above it, I'm kind of thinking of the abstract picture. This is like kind of, I've just got an abstract surface, and then in this remark, I'm thinking of everything living inside some ambient four manifold that's closed and simply connected. And this kind of perspective I'll switch between a few times, and I'll try and make it clear when I am, but the notation might be a bit, so that should be a prime, and maybe just put a prime there. Hopefully it'll be clear anyway. But if not, then yeah. Okay, so let's kind of give ourselves a goal. So the goal is to find some W to the 4 with pi1 of W non-trivial, the boundary of W equal to Y, and such that when we glue W and N over Y, it's simply connected. Okay, so this is then we'd be done, right? Because if we cut out N, that's like cutting by this remark, that's like cutting out the surface, and then the complement is just W, so that's going to have non-trivial fundamental group, and then we'll be done. Okay, so we've just kind of restated the problem as like a glue-in problem instead of finding something and cutting something out. That's kind of all that's happened here. Okay, so of course you might worry that there's an obstruction to being able to glue, and that's where the bordism comes in. So let's just talk about that very, very briefly. So for a group G, omega k of G, or the bordism group of G, in dimension k is pairs m to the k, so k manifold m and phi, where m is closed, oriented, k manifold, phi is a homomorphism, up to some cobordism relation. I'm just seeing this stuff in the chat. I need to. Oh, thank you for the clarification earlier. I just realized there was a chat. Okay, so for me, this is like, I'm not too worried about bordism, but I prefer it to be on familiar terms. So just kind of a well-known lemma. Omega 3 of G is just actually isomorphic in a natural way to the third homology of G. Okay, so that's pretty good, because I kind of come from a group cohomology background, so I'm in pretty familiar territory if we're just talking about group homology, whereas if we're worrying about Bordisms and four manifolds and things, like it's not bad, but it's it's like outside of my comfort zone, so it's better to be in the position where I can kind of use this. So that's good. So then the kind of the key lemma, I guess. So this is what we had to prove. Is the following. So it's going to give us a bunch of conditions where like we can guarantee everything we wanted in our goal. So I'm going to explain the lemma. I'll explain how it implies the goal. I'll show you some examples of groups where you can just plug it into the lemma, and then I'll prove the lemma. And that should be the whole talk. Okay, so we're going to have let P be a finitely presented simple group. We're going to have phi from pi1 of y to p such that, oh, okay, I'll say what mu is now. Phi of mu is non-trivial in p. Here, mu is the central element, is the generator. I guess that should be a generator of z of pi1 y. So this is a safe pi1 y is this safe at 5-bit space. So the key point was like if you take the circle bundle and you look at like the inclusion of the fundamental group of the circle into the fundamental group of y, this is actually central in that group. So it commutes with everything. And as it z, there's like two choices of generators. So I'm just going to pick one. And I just want this to be non-trivial in this homomorphism. Okay, so that's good. We want the Bordism class to be equal to 0 in omega 3 p, which is just the third homology of p. So if all of that holds, then there exists an embedding sigma to x such that I1 of x minus sigma, so rather interior of n, I guess, is what the proof gives, is isomorphic to B. Okay, so this kind of, the hypothesis is kind of what's going to give us the goal, and then we're kind of there. So I'll come back to the proof of the lemma, but first let's just see how it kind of gives you examples. So
sorry, I got lost for a second. What is x? Is it the point is there exists an x and an
yeah,
embedded?
yeah. So when I say there exists, I mean there exists an x, an embedded, smoothly embedded sigma, and yeah.
Thanks. Yeah.
Yeah, so the proof kind of constructs it all quite explicitly, but I'll prove the lemma in a few minutes. Okay, so how to apply the lemma. So there's kind of two examples. So the first one gives you an infinite group, and then the second one I'll give you a family of finite groups as well. So the first example is it's going to come from Thompson's group V. The Thompson's group V. And what this actually is isn't super important, but it's pretty widely studied in like mainstream geometric group theory, and certainly lots of generalizations of it show up everywhere as well. So this is kind of a pretty natural object for people to think about. And kind of one sentence, it's like, if you take the binary rooted tree, so you have a vertex and then there's two leaves coming out of every vertex. It's like the graph automorphisms of this graph. That's kind of one way to think of V. Or like finitely supported ones anyway. So this is kind of a nice natural kind of group that maybe shows up in like symbolic dynamics and stuff like this. But it has loads of really good properties. So firstly, it's finitely presented. Secondly, it's simple. Thirdly, it contains every finite group. And then a much more powerful result is that it's acyclic. So this says that Hn of V with Z coefficients equals 0. It's just a reduced homology. Okay, so who are these due to? So the first three is all due to Higman in 1974. And then this last result is due to Martin Seismic and Natalie Val. And this showed up in Inventiones a couple of years ago. So this is very recent. And this is like a very non-trivial result. The paper is really cool. Like it goes via some K theory of categories, and like there's some homological stability stuff going on. It's a very very clever proof. I've never seen group cohomology computed this way before. It's quite miraculous. I recommend everyone at least has a look at it at some point. Anyway, so this kind of has all of the stuff we might want, because if we have a map going to the third homology of V, then it has to be 0 because V has no third homology. So this kind of is a good trick. So all we have to do is find a map from the fundamental group of the safer fibered space to V, and we're pretty much home. So you ask, well, how on earth do you find a non-trivial map? And the trick is residual finiteness. So by Hempel, 1987, and pi1 of y is residually finite. So what does that mean? This means for all G and G non-trivial, there exists a finite quotient which only depends on G, so alpha G from G onto some finite group Q, where this is finite, such that alpha G of G is non-trivial in Q. Okay, so this just says that there's some every element for every element there's some finite quotient where it has non-trivial image. Okay, so how does this help us? Well, this means in our case there exists a finite quotient. Let's call it H from pi1 of y into some group Q, where the meridian doesn't die. So that's good. But the thing is Thompson's group V contains every finite group. So it didn't matter what this finite group was, we just embed it into V. So we can take this composite map where we go, so we can include Q into V, some map I, and define this I to just be this composite homomorphism. And now since V is acyclic, y and phi equals 0 in this third Bordesson group. Okay, so that would be done. Then we're done. This tells us there exists some manifold with fundamental, well, there exists a manifold X, the surface sigma, and when you cut out sigma, the complement has fundamental group V. So that's good. That's a really strange manifold, presumably. We didn't try and work out how many handles you'd need. I assume it's quite a lot because the proof kind of does surgery a bunch of times. But we'll come back to that in a moment. So maybe just kind of one other example. It's kind of the same sort of trick. Instead, you suppose sigma dot sigma equals n, and p divides n with p prime and p at least 7. Okay, Then there's two facts. So fact one is pi 1 of y surjects onto z mod p, and mu survives. I'll actually send it to the generator. And the second fact is that H3 of PSL to P with integral coefficients has no P torsion. Okay, for P at least 7. So now it's kind of the same trick. We take the composite map where you go pi 1 y, maps onto z mod P, and then you just map this into PSL2P. And then this composite is going to be the map we use to construct the manifold. That's picking a topological representative. Okay, so there's some finite groups, which I don't know, maybe that's a bit nicer in some way. I don't know what happens if you take the universal covering of this thing and then play the same game, because it's still going to be a closed, simply connected 4 manifold in some sense, if you like glue a bunch of them. Maybe that doesn't make sense. Anyway, so there's a bunch of examples. There's actually, you can define like Vn, there's some like generalization of V, and if you pick the finite quotient a little bit more carefully, you can actually get any one of these as well. So that's quite cool. Okay, so let's prove the lemma. I'll remind everyone what it says as well, because we've scrolled down quite a bit. So proof of the key lemma. So let's just go back up. So it said P was a finitely presented simple group. We had some map from pi 1 of y, this safe at 5 space, to P, such that the meridian survives, and the borders and class vanishes. Then we get this simply connected 4 manifold X and a embedded surface whose complement has non-trivial fundamental group. Okay, so I'll try and scroll up and down a couple of times so that we can remember what it said. Okay, so by the Bordism hypothesis, sorry, there exists W0 to the 4 such that have the following diagram. So we get pi 1 of y. We have phi going to P. We have some map going to pi 1 of W0 and some map here, phi 0. Okay, so this is just the Bordism relation. And now we're going to define a bunch of stuff. So we're going to say WP to the 4 is a 4 manifold with pi 1 WP equal to P. I guess I didn't need to say it was a 4 manifold. And we're just going to do some connect sums. So note pi 1 of W0 connect sum WP is just going to be pi 1 of W0 free product P. And this has a retraction onto P. So that's good. So you just kid everything. Okay, so we can do surgery. To kill pi 1 of W0 and obtain some manifold W1. So this is going to give us this kind of next portion of the diagram. This is pi, we get pi 1 of W1. This has a map here. And we yep, that's all good. Yep. And then we're going to kind of do the same thing. We're going to kill the kernel of phi 1, which is this map here. That's where I put the label. Okay, So we have this map here, we've called it phi1. We're going to do surgery again to kill the kernel of this thing, and obtain some manifold W and an iso phi. Number 2, let's make it yellow, orange. So we have I1 of W, we get this isomorphism here, which we call phi. And I guess the concern is that this kernel might not be finitely generated. In fact, it's a free product, so it almost certainly won't be. But the point is it's actually finitely normally generated. So when you do surgery, you kind of, you attach handles, at which in my brain is just like attaching disks. And when you kill like a loop, you actually kill the entire conjugacy class. So like if you're finitely normally generated, that's kind of the same as attaching finitely many disks because you've killed all of the conjugacy class. So there's nothing too much to worry about there. Now by assumption, we have that phi of mu is not equal to 1 in P, but P is simple. So this actually normally generates P. So this is really the only place that we use simple. It's probably possible to weaken it. I think like, you need at least that the abelianization is cyclic. And there's some conjecture of Weigand which asks when a perfect group, so a group with trivial abelianization, is generated by a single element. So this is kind of gets back to these old combinatorial group theory questions. But if you're simple, then you're normally generated by every element, so that it doesn't really matter. So just for ease of reading, we didn't kind of push this too far. But since P is simple, we have this. But mu is trivial in pi1 of n, because pi1 of n had this disk that was killing the meridian, because it was the disk bundle, if you thought of it that way. So actually, like, we're going to end up killing P is the point. So we have a pi1 of x. By Van Kempen's theorem is pi1 of W union over Y with pi1 of n. But this is trivial, so then we're happy. Cool. So that's how to prove the lemma. I realize I'm maybe slightly under schedule. So I don't have more to say, so unfortunately you won't quite get your money's worth, but I'm happy to chat and answer questions and things, so maybe we just do that. Thank you.
Oh, thank you. Let's thank the speaker. I should have just been a little bit later, and then it would have ended on the hour. So are there any questions from the audience? One question I have is, I mean, do you have any idea which groups can arise as a complement of as pi1 of complement of sigma? So I mean, I can follow from, like, the explanation was very clear, so I can kind of understand what these groups have to satisfy in order for your argument to run. But do you have any idea? Yeah.
Yeah. So. I mean, my guess is you need at least cyclic abelianization, and you need this like normal generation property, I guess. Beyond this, I'm not really sure like what else you kind of need. Because it kind of comes down to this like vanishing homology condition, and like, yeah, we've kind of found some artificial situations where you can guarantee it, but like it's possible it could happen naturally in some weird situations too, because you can probably find maps where it's 0. We left as a question which like finite simple groups you could get, because I thought that might be maybe a bit more tractable. if you kind of restrict it to something that's classified. And we tried to work out which sporadic groups could show up, but their third homologies weren't known in every case, so we kind of gave up at some point. But that was quite fun, just kind of finding all of this information in the literature. I saw there was a question in the chat too, so maybe I'll quickly answer that. So Alexis, the reason is by hypothesis, you've assumed the map is non-zero. That's really it. And then because this all commutes, it doesn't matter which way around you went, it still had to be non-zero. But the fact that var mu. Oh, I see what you mean. Sorry, I was misreading the question. The point is that in N, you've glued a disk onto the homotopy class corresponding to mu. So it's actually killed in N rather than in P. Does that help? Because N is this disk bundle, so like the circle has a disk on it, so it had to die.
We may have to guess what Alexis is thinking. I don't know. Okay. Are there other questions? If not, then I think we should thank the speaker again. So German wave. And then we can stop the recording and chat for a few minutes.
Cool.